Hi friends, in this video we will study about Bode plot. First I will try to relate Bode plot with the help of Nyquist plot. In case of Nyquist plot, what we do in the S-plane, first of all we have a open loop transfer function GSHS. Actually Bode plot is not much different from the Nyquist plot, so I will start Bode plot with the help of Nyquist plot and I will try to explain similarity and dissimilarity between the two plots. So first we have a transfer function GSHS. Let's say we have some transfer function S plus Z1 divided by S plus Z divided by S plus P1 into S plus P2, 1 0 and 2 pole system. So to draw the Nyquist plot, what we do in the S plane, we move from 0 to infinity. This is imaginary axis, this is real axis. In the Nyquist plot, what we do, we put S equal to, first we move on y-axis. So on y-axis what is S? On y-axis S will be equal to j omega, and if you will move from origin to infinity, omega will change from 0 to infinity. So while doing this, if you will draw the Nyquist plot, in the Nyquist plot we draw graph between imaginary part of GSHS versus real part of GSHS. So if you are on y-axis, the corresponding plot in the Nyquist plot, or the corresponding graph in the Nyquist plot, is called polar plot. If S is equal to j omega, omega varying from 0 to infinity, the plot in Nyquist plot will be called polar plot. So in case of Nyquist plot, what we do, on j omega axis we vary this quantity, the angular frequency. Omega is variable and imaginary part of GSHS, this will be nothing but imaginary part of G, S will be j omega, Hj omega, and here we will have real part Gj omega and Hj omega. So both real and imaginary part will be function of omega. So as we will vary omega, real part and imaginary part will vary, okay, and corresponding to each omega we will plot real part and imaginary part of this. Let's say for some omega we have this much, this is the point. For some other omega we will have this point. So this way you will have a plot. This will be polar plot. Okay, so in this graph, on x-axis we have real part, on y-axis we have imaginary part. Although omega is variable, but in this graph omega is not visible. We don't have any axis for, because we already have two variable quantity, okay, and we are drawing on two-dimensional plane, okay, so there can be only two variables. So omega is not shown in this graph. In case of Bode plot, what we do, on x-axis, on the horizontal axis we always put omega. In case of Nyquist plot, if we have Gj omega, a complex function of omega, it will have two parts, real part of Gj omega and imaginary part. Okay, so this kind of representation is called rectangular. This is rectangular representation, or this representation is in rectangular form. Suppose for some omega we are on this point, so this length will be real part of Gj omega and this length will be imaginary part. So this is one kind of representation in which we take real part and imaginary part, the two lengths. To uniquely represent this point, the another way of representation is to take distance of this point from origin. This will be called magnitude of Gj omega. The another way of representation of is magnitude of Gj omega Hj omega. But there can be many points at the same distance. If you make a circle of this radius, you can have infinite number of points. So to represent this point uniquely, you need one more quantity, and that quantity is angle, anti-clockwise angle from x-axis. Okay, so the another quantity is angle of Gj omega Hj omega. So there is one representation in which we take two lengths, one length is this and other length is this, that is rectangular representation. Another way of representation is in which we take one length, that is magnitude, and magnitude is nothing but distance of point from origin, and the another quantity is angle. And what will be that angle? Angle will be from x-axis in anti-clockwise direction. Suppose this angle is 30 degree, so angle of Gj omega will be 30 degree. If the point is here, let's say angle is same, but you moved in clockwise direction, so the angle of Gj omega will be minus 30 degree. So this kind of representation is called polar representation, in polar form. This is rectangular form, this is polar form. So even in Nyquist plot, we can have, for each omega we can have magnitude and angle. So in case of Bode plot, what we do, instead of plotting real part of Gj omega versus omega, what we do, we have here the magnitude of Gj omega Hj omega versus omega. This is called Bode magnitude plot, and the another plot is angle of Gj omega Hj omega versus omega. Okay, so this is the basic difference between Bode plot and Nyquist plot. In both the plots, what we do, we change the, we have to see the variation of Gj omega Hj omega, but in case of polar plot or Nyquist plot, the axis, on the y-axis we have imaginary part of GSHs and x-axis real part of GSHs. In Bode plot, in the Bode magnitude plot, we plot the magnitude of Gj omega Hj omega versus omega, and in Bode angle plot we have angle of Gj omega versus omega. So this is the basic thing. We will do some modification. This is not the Bode plot is not as it is in the final form. To go to the final form, we will do some modifications. Okay. But this is the basic difference between the two plots. Let's say we have a transfer function gs equal to 10 divided by s into s plus 5. And for this transfer function, let's say we have to plot modulus of Gj omega versus omega, the variation of magnitude of this quantity, okay, versus omega, the variation of this quantity with the frequency. Okay, so what we will do, we will write, if we put s equal to j omega, this is also called frequency response. Frequency response Gj omega, this will be 10 divided by s equal to j omega. Now if you want to take magnitude of Gj omega, we will have to take magnitude of this quantity, 10 divided by magnitude of denominator. Okay, if you have a quantity a into b, magnitude of A into B will be magnitude of A into magnitude of B. So magnitude of this quantity will be magnitude of this quantity, that is omega, and magnitude of this quantity is real part square plus imaginary part square. Okay, so you have a function. By varying omega we can get the plot. Okay, but if you are, this will be called the exact plot. You have a exact function of magnitude of gj omega, and by varying, although this function looks difficult to plot, but this will be exact function. But in case of Bode plot, we don't plot this way. We don't plot the exact function. Instead, in Bode plot we do some approximation. So what we will do, there are some modification in Bode plot. There are two basic modification. So in Bode plot, what we do, we don't exactly plot this graph. Instead we do approximation. I will discuss it little later. Now again, coming back to this example, g is equal to, or gj omega equal to 10 divided by j omega into 5 plus j omega. So this is corresponding to 10 by s into s plus 5. This can be written as 10 into 1 by j omega into 1 by 5 plus j omega, and this will be corresponding to 3 transfer function. There is one constant, another transfer function is 1 by s, and another component is 1 by s plus 5. Now in the further discussion we will find that, or you will be, if you compare this example with the example of 1 upon s only, plotting Bode plot or plotting magnitude of gj omega versus omega for 1 upon s only is very easy. What will be 1 upon s? This is 1 upon j omega, and if you take magnitude, what you will get? 1 upon omega only. Okay, so we will observe this in the examples also, that plotting Bode plot or plotting this graph for individual block is very easy. Okay, then why not to plot individually and then multiply it? Okay, this can also be done, that plot 1 upon s plus 5 and multiply it. Plotting 1 upon s and 1 upon s plus 5 individually is okay. Let's say you have two graphs. One graph is this, and another graph is, let's say you have this is another graph. So if you have plotted individually, but multiplying two graphs are very difficult. Okay, instead if you have to add two graphs, that will be easier. But what we are finding here, we have to multiply 3 blocks. We have to multiply 3 functions. This is gj omega. What will be the magnitude of gj omega? Magnitude will be 10 into 1 by omega into 1 by root under 25 plus omega square. So you have to get rid of this multiplication. Okay, that can be done very easily if instead of plotting magnitude of gj omega, you plot log of gj, log of modulus of gj omega, or to gj omega hj omega I will write it GJ omega only. Okay. So to get rid of multiplication, what I am doing here, instead of plotting magnitude of GJ omega, I am taking log of this. So what we will get here, we will get log 10 plus log 1 upon omega plus log 1 upon root under 25 plus omega square. Okay. And if we calculate modulus of GJ omega or log of modulus of GJ omega in dB, what we will do, we will multiply it with 20. This will be 20 into log 10 plus log 1 upon omega plus log root under 25 plus omega square. Okay, so for what we have studied, instead of getting exact plot of modulus of GJ omega, what we do, we take log. Why we take log? To get rid of multiplication. Okay, if there are multiplication of many quantities, if you take log, a different quantity will get added. So first we take log, and the second thing is approximation. So here we will observe what approximation I am talking about. To get plot of 20 log modulus of G omega, what we can do, individually plot log 10, that will be very easy, then individually plot it, and get the addition of these three graphs. So if we try to plot this log 10, what we have to do here, in the plot we have to get graph of 20 log modulus of GJ omega versus omega. We will modify this axis. Okay, this is not actually omega, we have log omega here. Okay, so first what we need to do, we have to get graph of 20 log 10. What is 20 log 10? 20 log 10 will be nothing but 20. This is a constant. So we will get 20 dB constant here. This will give you in dB versus omega. The second graph is 20 log 1 by omega. 20 log 1 by omega. This will be nothing but minus 20 log omega. Now if you will plot minus 20 log omega versus omega, this graph will be logarithmic and this will give you a curve. Okay, so plotting that will be, even if you plot this, you have to get the addition, so that looks difficult. So instead of, if you plot 20 log omega versus minus 20 log omega versus log omega, this will give you a linear graph. Okay, here variable is log omega. Then what will be here? If on the x-axis we have x, on the y-axis we will have 20x. So if you plot minus 20x versus x, you will get a straight line. So instead of plotting 20 log of magnitude versus omega, what we plot? Log omega. So this graph will be like, okay, so these two are easy. Here for plotting graph of these two terms, I did not use any approximation, but for plotting of this graph we will use approximation here. So in the third graph we have to plot 20 log 25 plus omega square versus log omega, and in Bode plot we use approximations. So to get the approximation, first we will plot when omega is very less. We have to plot 20 log 1 upon root under 25 plus omega square when omega is very less, when omega is or omega square is much less than 25. So this will give you 20 log 1 upon root under 25. This will be minus 20 log 1 upon minus 20 log 5. This will be approximately minus 14 dB. Here we have log omega, and let's say here omega is very less. I will separately talk about x-axis when we take log omega instead of omega. Okay. So when omega is very less, we will have minus 14 dB. Okay. This is the boundary when omega is very less. Okay. What will be the graph when omega is very high? Let's say omega square is much greater than 25. So how the graph will look like? If omega square is much greater than 25, we will neglect 25 in front of omega. So what we will get? We will get 20 log 1 upon root under omega square. That will be 1 upon omega, and this is nothing but minus 20 log omega. Okay. Now how this graph will look like? For 1 unit of change in log omega, we will have, if this quantity changes for 1 unit, we will have a decrease of 20 dB. If this x-axis changes for 1 unit, when log omega will change for 1 unit? When change in log omega is equal to 1 unit, when change in omega is equal to get 1 unit change in log omega, you will have to increase omega 10 times. So if omega changes 10 times, we will observe this, we will do these things many times in examples. So to get 1 unit change in log omega, we need to increase omega 10 times. So this is called, increasing omega 10 times will be called moving 1 decade. So if you move 1 decade, the change in log omega will be 1 unit, and you will have a decrease of minus 20 dB. So if I say what is the slope of this graph? Slope will be minus 20 dB. This is the change in y-axis. And what is the change in x-axis? 1 decade. Because you moved 1 decade, then you got change of 1 unit in log omega. Anyway, so when omega is very high, we have 20 log omega. This is equal to minus 20 log omega. So you have to plot minus 20 log omega versus log omega, or this graph will be minus 20, let's say this variable is x, minus 20x versus x. So what will be the shape of this graph? The shape of this graph will be a straight line with negative slope. It looks like that this graph should pass through origin. Okay. Here it looks like this graph should pass through origin, or when log omega is equal to 0. But in Bode plot, it is not necessary that at this point only we take log omega equal to 0. On the x-axis, at any point, that depends upon the convenience. At any point you can take log omega equal to 0. Let's say here log omega equal to 0. So this graph will pass through this point. Let's say here log omega equal to 0, or omega is equal to 1 radian per second. So we got two graphs. for the two different cases. The first case is when omega square is much less than 25 or omega is much less than 5, and the second graph is when omega is much greater than 5. And in both the cases, in the first case we got constant line, in the other case we got a straight line with negative slope. Now if we plot the exact graph, how will be the graph? If we plot the exact graph 20 log 1 upon 1 plus this quantity versus log omega, the exact graph will look like this. But in Bode plot, instead of plotting this curve, we always prefer to, or we plot only a straight line. This is the actual graph. Okay, when omega is very less, the actual graph will tend to this line. Okay, when omega is very high, the actual graph will tend to this line, because this line is the graph of this quantity when omega is very high. Okay, so when omega is very high, this is the actual graph, and this will tend to meet this point. Okay, when omega is infinity, this graph and this graph will exactly meet each other and become parallel to each other. This line will overlap the dotted line, or we can say that the actual graph is asymptotic. Okay, suppose this is the line and the curve is like this. It seems that on infinity the curve will meet the straight line and become parallel to this straight line. So in this case we will say the curve is asymptotic to this line. Similarly, here what we can say, the actual graph is asymptotic to which graph? Minus 20 log omega versus log omega. How is the actual graph here? Here actual graph is asymptotic to 20 log 5 versus log omega graph. Okay, so this is the actual graph, but as I said earlier, in Bode plot we don't get the actual graph. Instead we only plot the asymptotes, the two asymptotes of the actual graph. The first asymptote is this and the second asymptote is this. That's why sometimes Bode plot is also called asymptotic plot. Plot of modulus of gj omega, or log of, you can take 20 log of this quantity. What I said, in Bode plot we get the two asymptotes, or depending upon the transfer functions we may have different asymptotes, and we only plot the straight line part or the asymptotes. Now we got the two asymptotes. Okay, we have two types of graph. First graph is constant line, the other graph is a straight line with minus 20 dB per decade slope. Okay, now we have to choose which asymptote we have to plot for which range, because initially this graph looks valid, and for high value of omega this graph looks valid. And what is the error? Here we will get this much of error, here this much of error. The point at which the two asymptote meets, at this point we will get the maximum error. okay, then the error will keep decreasing. So to decide which asymptote to choose, what we will do, we will plot the two asymptotes, and the point at which the two asymptotes meets will become the boundary to choose from the asymptotes. This will become the boundary. And how to get the boundary? Obtaining boundary is not very difficult, but here it looks difficult because I am going by the procedure. What is this graph? The point at which the two graph or the two asymptote meets, at this point for both the graph value will be equal. So we will say this graph is nothing but minus 20 log omega, and what is this graph? Minus 20 log 5. So what is the value of omega? Omega equal to 5 radian per second. So before omega equal to 5 radian per second, this is omega equal to 5 radian per second. The Bode plot will be the first asymptote, that is minus 20 log 5. And after this boundary, the graph will be minus 20 log omega. If you want to get the boundary, what is the basis for drawing this asymptote and this asymptote? When omega is less than 5, you have to choose from the two graphs, and you have two conditions: when omega is less than 5 and when omega is greater than 5. So what will be the boundary? When omega is equal to 5. Or why you are getting omega equal to 5? Because omega is square equal to 25. And why you have got this type of function? In S domain, what you have? S plus 5. This is why you have got j omega plus 5, then you got omega square plus 25, and this way you got omega equal to 5 as boundary. So this boundary is called corner frequency. Corner frequency. Okay, and this will be at pole, and if you have a 0, you will get a corner frequency at 0 also. Okay, so we will discuss what is the error at different point. At 1 or 2 point we will calculate the error also, but first I want to summarize what we have studied so far, and I'm going to write down, or I'm going to tell you what exactly the Bode plot is, because we made many modifications. Okay, so we took this transfer function 10 divided by s into s plus 1, and then what we did, gj omega equal to 10 into 1 by j omega into 1 by j omega plus 1, then 20 log modulus of gj omega, we got 20 log 10 minus 20 log omega, here we have 5, then minus 20 log or plus 20 log 1 upon root under omega square plus 25. This can also be written as minus 20 log root under omega square plus 25. Okay, so what is the asymptotic plot for 20 log 10? This is already a constant line. Okay, the first one is very simple. You have a height of 20 dB here, the constant height. You don't need to use any approximation here because the graph is already a constant line. What is the second graph? Minus 20 log omega. Second graph is minus 20 log omega versus log omega. Okay, when log omega will be 0, this graph will give you 0. Whenever log omega is equal to 0, then omega will be 1 radian per second. So in the logarithmic scale, or in case of Bode plot, the point of 1 radian is not fixed. Depending upon your ease, you can choose on x-axis, anywhere on the x-axis, you can choose the point omega equal to 1 radian per second. So let's say at this point we have omega equal to 1 radian. As I said earlier, I will explain the omega axis versus log omega axis later. So at this point we have omega equal to 1, then log omega will be 0. If log omega equal to 0, you will get 0 height, and you have a slope of, when you will change log omega by 1 unit, the dB will decrease by 20. You will have a decrease of 20 dB. The slope will be, this will give you a straight line, this will give you a straight line with slope minus 20 dB per decade. So here also we don't need any approximation. The third graph is initially, this is initially at minus 14 dB as we calculated before, and after omega equal to 5, let's say we have omega equal to 5 here, but the axis is log omega, so the actual point on the axis will be log 5. Okay, so up to log 5 we have a constant gain of minus 14 dB, and after this point the second asymptote is valid. Here we will have a slope of minus 20 dB per decade. Okay. Now what we have to do to get the Bode plot of this function, what we used, we took the log and we applied approximation. Since we took the log, what we have to do, we have to take addition of these three graphs. So if we want to take addition, we will first choose a point. Let's say when log omega equal to 0, we have to add these three graphs. So first calculate, for each value of omega we will take the value of this graph, value of this graph, value of this graph, and we will add those three values. So at log omega equal to 0, what it is giving? For each omega this is giving 20 dB. For log omega equal to 0, this is giving nothing, 0. So we have 20 plus 0. Since this point is omega equal to 5, so omega equal to 0 will be left to this point. So at log omega equal to 0 we will get minus 14 dB. So we have 20 plus 0 minus 14 dB. This is 6 dB. Let's say here we are at log omega equal to 0, or omega equal to 1 radian per second. In Bode plot, you will oftenly find that although the axis is log omega, but value of omega will be written at different points. Okay? That's why I have written, although value of axis at this point is 0, but value of omega is 1 radian per second, and you will oftenly find the value of omega will be written for different point. Okay, so at log omega equal to 0 we have 6 dB. Let's say this height is 6 dB. Now for the graph, if you got one point and then you know the slope, you can, this is sufficient information to draw a complete graph. You have got one point and if you know the slopes. So before this point, what is the slope? Before log omega equal to 0, this always gives a constant 0 slope. This always gives a constant slope of minus 20 dB per decade. And this gives a slope of minus 20 dB per decade after omega equal to 5. So if we talk about slope, what will be the boundaries? This always gives a minus 20 dB per decade. This always gives a zero slope. So if you will add these two graphs, here the slope is always minus 20, here the slope is always 0. So if you will add only these two graphs, the slope will be minus 20 dB per decade. But this has two types of graph. For omega greater than 5, you have a slope of minus 20. Sorry, okay, this is correct. And for omega less than 5, you have zero slope. And what is the slope of these two parts? The slope of these two parts is minus 20 dB per decade for each value of omega. Now you have to add slope of first two parts and slope of third part. So what you will have? For omega less than 5, this gives minus 20 and this gives 0. So we will say for omega less than 5, we have minus 20 dB per decade, and for omega greater than 5, this always gives minus 20, and for omega greater than 5, this again gives minus 20. So for omega greater than 5, we will have minus 40 dB per decade. Here we are at log omega equal to 0. Let's say the point is, this point is log 5, means omega equal to 5. So after this point, we will have minus 40 dB. This is a boundary for slope. You have a this point on graph. Before log omega equal to 5, you will get a slope of minus 20 dB per decade. And after log omega equal to 5, you have a slope of minus 40 dB. This is an increased value of slope. This is minus, increased means increase in sense of magnitude, minus 40 dB per decade, and here we have slope of minus 20 dB per decade. So this is we have drawn Bode plot for this transfer function. This is Bode magnitude plot. Bode magnitude plot. If you will calculate for log omega equal to 5, you will get 0. For log 5, this always gives 20 dB. This will give you minus 20. Put omega equal to 5, you will get minus 20 log 5, and this gives minus 14 dB. So this can be calculated as 0. So what we did to get the Bode plot of this, you will be given with GS. Then you have to find G j omega, then modulus of G j omega. Then take log and multiply with 20. 20 log modulus of G j omega, and separate the different transfer function to get the addition of those transfer functions. So you have to plot 20 log G j omega versus log omega with approximation, or you have to get asymptotic plot of asymptotic plot of 20 log modulus of G j omega versus log omega. This will be Bode plot. Okay, and there may be many asymptotes corresponding to each terms. So at which point which asymptote will be valid? So how you will find it? At which point which asymptote will be valid? You will draw all the asymptotes. Okay, and you will draw all the asymptotes, and where the asymptotes meets, where the two asymptotes meet, that point will be the boundary for validation for each asymptote. Or the boundary will be easily when we will do the further examples, in those examples we will observe that the boundary is nothing but the boundaries will be at poles and zeros, and the boundaries are also called corner frequency. Now I'm taking one more example to have a better clarity of the Bode magnitude plot. Let us GS equal to, instead of writing GSHS, I'm writing GS only. GS equal to 100 divided by S into S plus 10 into S plus 100. So what you will write? Gj omega will be 100 divided by J omega into J omega plus 10 into J omega plus 100. Then 20 log, or first you will take modulus of Gj omega. Modulus of Gj omega will be 100 into 1 by modulus of this into modulus of this into modulus of this, omega square plus 10 square plus omega square plus 100 square. Okay, then we will take log to convert these multiplication into addition. 20 log this will be 20 log 100. This will give you minus 20 log omega minus 20 log omega square plus 10 square minus 20 log root under omega square plus 100 square. Okay. Now individually plot 20 log 100 versus log omega, 20 log omega versus log omega, and add those graphs. This is the procedure. When you will have enough practice, you don't need to plot individually in one graph only. You can have the Bode plot. But here we will draw the individual plots and we'll take addition of those. So what will give you the 20 log 100? 20 log 100 will be, log 100 will give you 2, so 20 into 2, this will give you a constant of 40 dB. So we don't need any approximation here. We have already seen 20 log omega versus log omega. Let's say at this point we have log omega equal to 0. This point is omega equal to 1 radian per second. So at this point log omega is 0. So if log omega is 0, minus 20 log omega will be 0. And slope is minus 20 dB per decade. Then the next part. So here the graph, if you will plot the exact graph, this will not give you linear curve. Instead you will get a curve. You will not get straight line. So you will plot the asymptotic plot. So when omega is very less, what you will get? First, when will be the boundary? The first condition is when omega square is much greater than 10 square, or the first condition is when omega square is much less than 10 square. Then it will give you omega less than 10. Here it will give you omega greater than 10. There will be two asymptotes as we did in the previous example. So for the two cases we will have two asymptotes. The first asymptote will be valid in this region and the second asymptote will be valid in this region. So what is the boundary? The boundary is nothing but at the pole, or the corner frequency will be at pole. Here we have taken log omega equal to 0. And what is the boundary? Boundary is equal to at omega equal to 10. So when omega is equal to 10, what will be log omega? Log omega equal to 1. So at this point, the value of this axis at this point will be 1. So this is the boundary. Before this boundary or left to this boundary, asymptote corresponding to this condition will be valid. So when you have this condition, what you will do? You will neglect omega. You have to neglect this quantity or this quantity. And which quantity will be neglected? The quantity which is lesser will be neglected. It does not matter. It doesn't matter how much this quantity is less than 10. Even if omega is equal to 9.9, we will, although omega equal to 9.9 is very close to 10, yet we will neglect it. Okay. If any quantity is less than other quantity, doesn't matter how close they are, we have to neglect it. So if omega is neglected, what we will have? We will have minus 20 log 10. Okay, what is the minus 20 log 10? This will give you minus 20 dB. So before, this is the point omega equal to 10. Before this point, what we will get? Minus 20 dB. Omega equal to 1. And before omega equal to 10, we will get a constant of minus 20 dB. But when omega is greater than 10, even if value of omega is equal to 10.1 radian per second, now this 10 will be neglected and we will have omega square here. Omega square, the root will be cancelled with a square, so we will get the value of this quantity will be minus 20 log omega. Now on the x-axis, what we have? On the x-axis we have log omega, so the graph will be minus 20x versus x. So after this point, but this formula is valid only after omega equal to 10. So after omega equal to 10, you will get the graph of minus 20 dB per decade. You don't need to find out from which point this graph will start or this graph will begin, because we have already seen that the two graphs will always meet at corner frequency, and you already know the corner frequency. So you will start this graph from corner frequency only. So you have one point for this graph and slope, so you can plot it. Okay, the next term is omega square plus 100 square. So in the same way as we did in case of omega square plus 10 square, what will be the corner frequency? Corner frequency will be 100. Omega equal to 100 means log omega equal to 2. Here we have omega equal to 100. So before this, when omega is less than 100, what we will get? Minus 20 log root under 100 square. This is nothing but minus 40 dB. So before 100, what we will get? We will get a constant of minus 40 dB. Okay, and after omega square is greater than 100 square, or omega is greater than corner frequency, when omega is greater than 100, okay, then omega square will dominate, we will neglect this. So we will get minus 20 log root under omega square, or minus 20 log omega. So this graph will be minus 20 dB per decade. Okay. Now we have to combine, we have to add all these graphs. Let us choose a point first. let us find out the value of this graph at when log omega equal to 0. When log omega equal to 0, this will give you 40 dB, this will give you minus 40 dB, then we are at 0. This already gives 0, but this gives minus 20 dB. So what we have at omega equal to, at this point, 40 minus 40, 0, 0 minus 20 dB. So at this point we are at minus 20 dB. Now if we talk about the slopes, this always gives 0 slope. This always gives minus 20 dB per decade. But this does not give a constant slope. This also does not give a constant slope. So what is the boundary of slope? We get, for the first term, we get 0 dB per decade always. For the second, we get minus 20 dB per decade. For third, we get 0 and minus 20 dB per decade with boundary omega equal to 10 radian. For the fourth one, we get 0 and minus 20 dB per decade, and the boundary is omega equal to 100 radian per second. So we got two boundaries. The first boundary is at omega equal to 10 radian per second, and the second boundary is omega equal to 100 radian per second. If you have two boundaries, you will certainly have three regions. Two boundaries, first region, second region, and third region. So in the first region, this gives 0 slope, this gives 0 slope, this gives 0, and this gives minus 20 dB. So for the first region, you will have a slope of minus 20 dB per decade. Let's say this height is minus 20 dB. Okay. So in the first region, what is the slope? Minus 20 dB per decade means in 1 decade the graph will decrease by 20 dB. At this point, the graph is already at minus 20 dB, and this is 1 decade. So in 1 decade, the decrease will be further 20 dB. So we will be at minus 40 dB. Let's say this is 20 dB, this is also 20, this is 40 dB. From omega equal to 10 to 100, after 10, this gives a constant slope of minus 20, but this gives 0. So you will have minus 20 dB, minus 20 dB means minus 40 dB per decade. In this region, you will get a slope of minus 40 dB per decade. Means in 1 decade, here I have taken 1 decade. In 1 decade, the decrease will be of minus 40 dB. Here you are already at minus 40, and the decrease will be 40 dB. This height is 40 dB. So this will be the graph. And after that, you will further get, after omega equal to 100, this will also start giving a slope of minus 20 dB per decade. So the slope will be minus 20, and minus 20. Slope will be minus 60 dB per decade. So this is asymptotic or Bode plot of this transfer function. Bode magnitude plot. When you will have practice, how we will draw this graph, you will first, since I had to go by the procedure, but in the examination, when you will have practice, you will plot like this. First you will decide the corner frequencies. First you will decide a point. Let's say this point is log omega equal to 0 or omega is equal to 1 radian per second. Then you will decide corner frequencies. What are the corner frequency at omega equal to 10 radian per second and omega equal to 100 radian per second. So let's say this is omega equal to 10 radian and with the same length, the length will be in terms of decade. At 10 you are at 1 decade, at 100 you are at 2 decade, so the length will be same. This is omega equal to 100, this is omega equal to 10. Okay, and 1 upon s term, this always gives, you will have a 20 log 1 upon omega. This always gives a slope of minus 20 dB per decade. So you will say, after this point, after omega equal to 10, this will give a slope of minus 20 dB. After omega equal to 100, this will give a slope of, as we observed in this graph, after omega equal to 100, this will start giving a slope of minus 20 dB, and you have an initial slope of minus 20 dB. Okay, so initially you will start the graph with the slope of minus 20 dB, but to start the graph with minus 20 dB, you can have a graph like this, you can have a graph like this, you can have a graph like this. So you need to get at least one point. So initially get that point. When you will put omega equal to 1 radian per second, okay, you already know we have to plot an asymptotic plot or approximated plot. And what is the basis of approximation? The quantity which is lesser will be neglected. Okay, if you have a term of addition, here you have a term of addition, and also you have a term of addition. So here we will apply approximation, and what is the basis of approximation? The quantity which is lesser will be neglected. So if you will put omega equal to 1 radian, here j omega means omega will be 1 radian, so this quantity will be neglected and you will get 10 only. Here you will put omega equal to, this is j omega, this is j1, and here you have 100, so this will be neglected. So what you will get? 100 divided by, this is j omega, but there is no addition term, so you don't need to apply any approximation. This is j omega and magnitude will give you 1. Here this is neglected, you will get 10. Here this is neglected, you will get 100. So you got a magnitude of 1 upon 10, but you have to take 20 log of this, you will get minus 20 dB. So at omega equal to 1 radian, at omega equal to 1 radian, this is omega equal to 1 radian. So at this point what you got? You got minus 20 dB. You have minus 20, and you already have an initial slope of minus 20 dB. So this will be the graph. This is a corner frequency, and since you have a pole here, so slope will decrease. Then this is also corner frequency, the slope will further decrease. In further lecture we will talk more about axis, omega axis and log omega axis, and we will do some questions. The question may be like this: you will be given a Bode plot, you will be given a point on Bode plot, and you may be asked to find out the height in dB at some other point.